Hello, everyone. Boa noite a todos. Vamos começar a fazer nas duas línguas, em português e inglês, para apresentar o CBT, o CBMR, e depois a gente vai passar em inglês. So we're going to do in both languages here. We're going to do a little bit in Portuguese, a little bit in English, and then we switch back to English. Bem-vindo a todos para mais uma live do CBT, hoje em cooperação com o CBMR, e eu tenho aqui comigo a Dalma Cerro, representando o CBMR. E antes da gente apresentar as nossas convidadas, a Dalma vai contar um pouco do CBMR. So before we introduce our guests, we're going to talk a little bit about CBMR. That's our invitee as moderator for tonight. So, Dalma.
Boa noite a todos. Hello, everybody. Welcome to this webinar. Obrigada por chamar a CBMR nesse evento. Bom, eu vou começar um pouquinho falando sobre o que é o CBMR, né? The CBMR, well, my name is Dalma. I'm part of the young members of Brazilian Committee of Rock Mechanics, CBMR, and I'd like to make some comments on the committee. Well, first, the CBMR is affiliated to the International Society of Rock Mechanics and Rock Engineering, ISRM, and is linked to the Brazilian Association of Soil Mechanics and Geomechanical Engineering, ABMS. There are some purposes that CBMR has, and I'd like to highlight some of them this night. Well, first, the CBMR is bringing together all those who practice the rock mechanics and rock engineering in Brazil in any of their applications, such as civil engineering, petroleum, mining, and geology. Also, is maintaining a constant exchange with rock mechanics expert and technical associations in the international scope. And also is encouraging scientific and technological research, doing collaboration with universities, research centers in rock mechanics courses that they usually organize. And finally, as a young member, the CBMR is doing actions to engage the young people in some activities such as Rock Ball, which is a quiz on rock mechanics, and also is bringing the CBMR award. Well, let me continue talking about our board of directors, which is headed by Marcos Massal as president, Thalita Miranda as vice president, Tiago Borges, which is our general secretary, Alice Estel, which is the financial director, and finally Daniel Melo, which is who is the director of technical events. I'd like to talk a little bit about the young members. Currently, we are 4 members, but there are 6 more people in training, and they will be joining us probably in June. These are some corporate associates to the CBMR, Joe Brook, Macaferry, Belgo, G5 Engenharia, and Incotep. And well, as a committee, the CBMR has presence in some events and organizations around the world. Some of them are the Cobranssec and Slope Stability, which is happening on 2024, next year. And also the CBMR is organizing the Latin American Rock Mechanics Symposium on 2026, and also is bringing into institutional support for the INFUM, which is happening this year in October. Finally, as an introduction, I'd like to share our social media with all of you. This is our site, and also you can find us on LinkedIn, on Instagram, and also on Facebook on these links. And we have delight if you follow us on all of these channels, and also we update with all the things about rock mechanics. Bom, thank you very much, obrigada. Foi uma pequena introdução sobre a CBMR.
Thank you very much, Alma. Obrigada. So before I introduce our speakers, please, if you have not done so, give like to the video, follow our channel, because we are providing presentations in Portuguese and also in English. We have past presentations. There's a high variety of subjects in tunneling. So I think we are ready to introduce. We have two colleagues here. I'm very happy to receive them because they are colleagues from where I also did my PhD at Queen's University with all of the same supervisor, Professor Mark Digeritz. So they're going to talk about the application of calibrated multiscale numerical models for rockburst, hazard in mine and tunnels. So with us, we're going to have Dr. Kati Kalenchuk, and she has over 15 years of experience in geotechnical and geomechanical engineering, providing due diligence and third-party reviews for geotechnical design, induced seismicity, and numerical modeling studies. She has extensive experience in underground mining, operational rock engineering, and ground control. She's an expert in high-end numerical modeling. And then we have Dr. Neda Dadazadeh. I hope I said right. She's specialized in geomechanical engineering, including numerical modeling to predict ground response to excavations, geomechanical mine design and optimization of ground support for tunneling and mining. She's experienced in characterization of rock burst and brittle fracturing in hard rocks through seismic data analysis and advanced numerical modeling. Her PhD research was focused on the numerical assessment of stress-induced damage in deep geological repositories, which gave her particular skills in developing calibrated models for predicting rock engineering issues related to deep excavations in hard rock. And both, they are part of Rockeng, that's in Kingston, a company in Kingston. Rockeng provides specialized consulting service to the mining and civil industries. Areas of expertise include rock engineering for underground and surface excavations, ground support design, numerical modeling, landslide mechanics, mine backfill and barricade, geotechnical monitoring, and site characterization. Since incorporation in 2010, they have grown into a global consulting firm with projects across Canada and around the world. So I welcome both of you to our live, and I would like to know who is going to start so then I can share the correct slide. It's named, right? Isn't it? Okay. So welcome.
Thank you.
Okay, so you just let me know when I should change the slide, okay? So please, the floor is all yours.
Sorry, I think you.
Is the wrong slide? Is the wrong...
Kathy is going to start first.
Sorry. I got confused. Okay, now it's right? Yes, okay. Okay, so we are here in the background. Please, the floor is yours.
Thank you very much for the invitation to speak today. It's a pleasure for Neda and I to present this work on using multi-scale models for rockburst hazard management. When we are working to develop effective strategies for managing geotechnical hazards in tunnels and mines, requires an understanding of the spatial and temporal distribution of ground reaction mechanisms. Numerical models provide a means for us to make forward predictions of ground reaction, and the calibration of our numerical models ensures that we have reasonable confidence in forward predictions. Further to making predictions of ground reaction mechanics, the process of numerical model calibration also provides very valuable opportunity to improve our understanding of logical controls and factors. So our presentation today start with an overview of modeling objectives and multi-scale modeling concepts. I'll speak to model inputs and uncertainties, overview, calibration data, and then Neda is going to present a case study on scale Rockburst hazard analyses. We'll wrap up with some closing comments and an opportunity for questions. The application of numerical models in geotechnical hazard management can be broadly classified into two groups: susceptibility modeling and mechanistic modeling. Susceptibility modeling investigates the likelihood that a geomechanical system will be exposed to a particular ground reaction. And this requires global project scale stress models, where our scale of interest is in the order of hundreds to thousands of meters. Often, global susceptibility modeling relies on either mechanistic analyses or empirical correlations to predict failure mechanics. Mechanistic modeling aims to improve our understanding of fundamental mechanics, and this becomes critical for tunnel scale analyses. Our scale of interest for mechanistic analyses is in the order of tens to hundreds of meters, and the enhanced model resolution that is achieved improves our representation of constitutive models, and it also improves our ability to simulate the interaction of ground support systems with the surrounding rock mass. When we develop strategic and tactical strategies to manage geotechnical hazards in mines and tunnels, we often rely on multiscale modeling. Multiscale modeling is a process where we make use of both global susceptibility models as well as local mechanistic analyses. The first step is often to do project scale modeling to provide a susceptibility forecast for global and local scale hazards. The second step is often local scale mechanistic analyses, and these must be coupled with our project scale understanding so that the local scale mechanics can be evaluated with an understanding of broader control or broader geological controls on boundary conditions and material competencies. Once we have a holistic understanding of global geological controls on stress and material domains, a picture of project scale stress, strain, and state evolution, and a local understanding of hazard mechanics, interpretation of the spatial and temporal distribution of hazard intensity can be achieved. So these combined global and local efforts facilitate informed decision making when we want to develop and implement risk mitigation strategies. When developing numerical models, we need to consider various inputs, and these include excavation shapes, geological domains, geotechnical domains, and our boundary conditions. These model inputs are achieved from a variety of data sources, and our level of confidence in each of these inputs is variable. The excavation shapes are often based on design solids or surveyed as-built, and we generally have fairly good confidence in model geometries for most modern applications. Geological modeling and geotechnical modeling rely on similar data types. We often look to mapping data or drill core logging, and possibly the use of geophysics or other instrumentation. Loading conditions or boundary conditions tend to have the most unknowns, particularly in situ stress state, which is often a very data limited component of our site characterization. Over the scale of an entire project, we tend to have very few measurements of stress state, and this is due to the inherent costs and difficulties in achieving reliable measurements of a global stress tensor while capturing also local variability. Model calibration is the process of correlating observations of actual ground behavior with numerical output, and this helps us to refine numerical inputs. The back analysis of observational data is fundamental to achieving confidence in the inputs that we apply to a numerical system. So what's important here? First of all, we need to have an understanding of our geological domains, geotechnical domains, and our global stress state. And where observational data is available, model calibration is critical for all components of our inputs. We have to calibrate not only material properties, but also our boundary conditions, also our constitutive models, and in some cases, we actually have to calibrate our input geometries. There is a broad spectrum in the level of calibration detail that can be achieved, from qualitative ground response to sophisticated quantitative calibration. The level of rigor and detail of calibration is dictated by our data that is available. Qualitatively calibrated models provide us an indication of different classes of behavior under varying loading conditions, while quantitatively calibrated models provide direct indications of likely rock mass stress and strain behavior. Both of these approaches facilitate risk management. However, quantitatively calibrated models typically have reduced uncertainty, which means that we can optimize our design and often work with lower factors of safety. Quantitatively calibrated modeling is exceptionally difficult to achieve because it requires very high quality instrumentation data. Now let's look at a few different types of calibration data. The most rudimentary form of calibration data is visual observations of ground reaction. In this case, we have no real measurements of deformation or state, and so our calibration is limited to very qualitative means. I have a simplistic example shown here on the screen whereby damage mapping observations allow us to make a comparison of damage intensity to numerically predicted stress or strain states. A well-calibrated model would conclude that similar loading conditions for similar damage observations can be correlated for any particular geotechnical domain. It is important to recognize that if we have to rely on visual observations, that they are not providing direct measurements of constitutive behavior. Once a rock mass has any visible evidence of yield, it's impossible to know where that rock mass is on the stress strain path. And this is a very significant limitation to model calibration. And it is very difficult to define the shape of our stress strain path and almost impossible to accurately do post-peak parameterization. A few examples are shown here on the slide. The top image is conceptually illustrating that damage observations, in this case in the top and back of, or in the tunnel walls and in the back of a tunnel, conclude that a rock mass is post-peak. But it provides no further information. This is a very black and white situation. The rock mass can only be classified as failed or not. The schematic on the bottom demonstrates conceptual probe holes. Geotechnical practitioners often rely on probe holes to observe damage depth around the periphery of an excavation. This provides a bit more information than visual observations of superficial conditions alone. However, we still do not have any direct measurements of loading conditions or strain accumulation. Model calibration is improved when we have access to data from conventional instrumentation. Instrumentation provides physical measurements of rock mass stress state and strain accumulations. Stress and stress changes can be sampled by various types of stress cells or geophysical methods, and strain is measured by either superficial or borehole deformation monitoring. And there's a number of examples shown on the screen here of different types of monitoring systems, ranging from radar or laser scanning systems through to borehole instrumentation. When we work with conventional instrumentation to calibrate numerical models, the process is actually very straightforward. because we have physical measurements that can be directly compared to numerical output. What I have shown on the screen here is an example of an underground pumping station. Unfortunately, this particular pumping station has accumulated some damage due to squeezing of the walls. We can see in the photographs there's some cracking in the concrete liner and some floor heave in the excavation. So in this case, the pumping station has several monitoring points along the main chamber, and those monitoring points could be used to measure closure and correlate it to numerical models. So the main chamber is illustrated here in the numerical model geometry by the red and green excavation. And along the axis of that excavation, we're monitoring closure. So some data can be directly compared from real life to the numerical model. And what we have shown here in the bottom right-hand side of the screen is monitored closure, so physical measurements, compared to modeled closure, which comes from the numerical model. And we can make direct correlations on goodness of fit. There are a few challenges that we must acknowledge when we're working with conventional instrumentation data. First of all, spatial resolution. It is nearly impossible to get a fully three-dimensional picture of stress and strain unless we have really big monitoring budgets. Individual measurements provide information at specific points in space, and practitioners have to be careful to ensure that they are understanding whether particular observations represent a global ground response or a localized mechanism. A second challenge in conventional instrumentation is that our goal is to capture measurements of the complete stress strain path of a rock mass. And we very often do deformation monitoring, but less often we do stress monitoring. And so we don't get the stress component of the ground reaction, typically. The third challenge is temporal coverage. Instrumentation is commonly installed after some amount of rock mass damage has accumulated. This is particularly true in mining, where instrumentation is often used reactively rather than proactively. The third type of calibration data that I would like to mention is microseismic data. Microseismic monitoring is much more common in the mining industry than in civil projects. Seismic data provides us a fully three-dimensional volumetric representation of where the rock mass is transitioning through the failure process. And it also characterizes the energy that is released during fracturing and deformation. What I have shown here in this slide is a long section view of a mine. All of these red lines are different tunnels in the mine. And all of the colored dots or circles that we see are seismic events that have been measured by the monitoring system. And so you can see some areas have no seismic events occurring. This would be areas of the rock mass that is not actively failing. And where we see lots of clusters of seismic data, it is indicating to us that our rock mass is going through the failure process. And so we know that the onset of seismicity occurs well before peak strength. This is generally correlated with crack initiation at the laboratory scale. Seismicity will generally ramp up in intensity as we approach the peak strength of a rock mass. And then post-peak, we will continue to see some seismicity until a rock mass becomes aseismic, at which point we know that we're in a residual state. So with this knowledge, we can effectively map spatially where the rock mass is transitioning through a failure process. Seismic data can provide an opportunity for both qualitative and quantitative model calibration. And this is generally dictated by the quality of our seismic data that's available. On the left-hand side of the screen, I have an example of qualitative calibration using seismic data. And in this case, we are just mapping seismic events visually to numerical outputs. What I have shown here is a cross-section through a numerical model of an underground mine. The pink that we see on the screen is all of the mining tunnels that have been constructed. The brown area through here is the ore body that has been extracted through the mining process. The light blue elements show us where the rock mass is pre-peak, and then the green and the red elements are illustrating regions of the rock mass that are post-peak. I have overlain seismic data that is from this particular site, and all of those black dots are representing individual seismic events. So those black dots are telling us where the rock mass is going through the failure process, and we can compare that to our numerical output. It's very qualitative and somewhat subjective. When you have good quality seismic data, there is excellent opportunity to achieve quantitative model calibration. And this is done by using our seismic data to sample the stress, strain, and yield states within a numerical model. And for any particular geotechnical domain, the model state should be statistically repeatable where seismicity is happening, because the material properties are constant within an individual domain. We expect rock mass failure to occur under reasonably consistent loading conditions. Now, going back, let's recall that geomechanical hazard analysis relies on both global susceptibility modeling and local mechanistic modeling. And it's important to recognize that the calibration process, the inputs and the outputs will vary quite significantly depending on the scale of your simulation. If we look first at global model calibration, we generally require ground reaction data that's available for a large portion of the project volume. Therefore, we generally require seismic data or deformation data with broad spatial coverage in order to achieve calibration. So here's an image showing seismic data around an underground mine. Large slopes we monitor with radar systems, so that gives us deformation monitoring over a large area of our interests. And evolving technology using LiDAR and scanning tools in underground excavations allows us to achieve broad spatial coverage of deformation monitoring in underground excavations. At the global scale, calibration testing commonly focuses on domain conditions and the influence of both boundary conditions and material competencies. So in my experience, testing should prioritize a focus on numerical model inputs where we have the greatest uncertainty, and that provides the most significant added value to our modeling project. And of course, our greatest uncertainties are often situated around loading conditions, boundary conditions, and in some cases, geotechnical parameterization. So in most cases, as I said, the largest unknown is in situ stress state, and methods for how we initialize boundary conditions in a numerical model can have a substantial impact on the quality of our calibration. So let's look briefly at a few different methods for applying in situ stress to a numerical model. Consider here that you have an underground mine, and we have to think about what types of data might be available. There may be a conceptual understanding of regional in situ stress trends, maybe based on tectonic history. And if we're lucky, we may have a few local measurements of in situ stress from our project area. The most common method for initializing in situ stress in a global project scale model is to simply initialize kind of our average boundary conditions, sometimes with gradients associated with depth. An alternative method for initializing stress is to use strain-based stress initialization, and this allows us to capture stress state gradients that are associated with stiffness contrast between geotechnical domains. With this method, strain is induced within the numerical model, which is reasonably consistent with the site geological history. And it allows stress within individual geotechnical domains to come to a more natural, non-uniform state. So to simplify this, you can consider a system of springs. If you apply a constant deformation to two springs with varying stiffness, the required force to achieve that deformation varies. So hence we are effectively squishing and squeezing our numerical model until we have a representative stress state. Here is a very simple case example to demonstrate how the stress initialization process can influence virgin stress state. Here we have an underground mine shown in the top left-hand corner of my monitor. The gray that is shown is all of the mining tunnels and the mined out ore body. And there's a cross-section cut through here showing 3 different geological units in blue, red, and green. Now, when you initialize numerical stress, there's 2 methods: a uniform depth gradient, which is shown by these cross sections on the center portion of the screen. We can see stress magnitudes increasing with depth. And the alternate case would be strain-based stress initialization. So here we can see there are 2 wildly different results for the stress initialization. And Dr. Dadashizade will demonstrate later the importance of this in our mechanistic analyses. Now, jumping back to local model calibration rather than the global calibration, we know that the ground reaction observations have to be much more detailed. And so we generally lean on using conventional instrumentation to calibrate our local mechanistic analyses. So last statements here before I hand the floor over to Neda. I just like to point out that in summary of model calibration, it is critical to calibrate our models in order to have confidence in making forward predictions. But the value in model calibration goes well beyond predicting and value opportunity. At the global scale, we strengthen our understanding of broad geological. We improve geotechnical domain, and we improve confidence in our boundary conditions, as well as allowing for mechanistic domaining. At the local model scale, calibration allows us to improve confidence in our constitutive behavior. It provides explicit evaluation of failure mechanisms, and it reinforces our understanding of geological controls on ground reaction. And now we're going to switch over, and Neda will demonstrate multi-scale modeling through a case study.
Thank you, Dr. Kalanjak. Okay, so for the rest of this lecture, I'm going to present a case study where a large magnitude rock burst in a deep mine tunnel was back analyzed with numerical modeling using FLAG3D. So during the presentation, I will first briefly touch on some background of rock burst failure mechanisms. So if there are people from different backgrounds, hopefully will follow the talk easier. And then I will go over some background of the case study itself, and then we will look into details of the numerical model, how the ground reaction was interpreted, different ground reaction indicators, including support performance, will be analyzed. And finally, we will summarize the causal factors and conclusions. So sudden deformations occur in hard rocks under high stress conditions, which this ground response induces seismic events that result in energy release in the form of seismic stress waves and seismicity. So as a reference to get a feeling, the excavation-induced seismicity is somewhere between the large magnitude events that are induced by earthquake activities and the microseismicity that are typically measured by acoustic emission tools. So excavation-induced seismicity in deep excavations are somewhere between these ranges. So rock bursting is a widely recognized hazard in high-stress excavations, which specifically refers to sudden and violent failure of a volume of rock that is associated with a seismic event. So on the left figure, you see an example of a rock burst ahead of a TBM machine. And on the right, you see a major failure of mine tunnel, which we will focus shortly in this case study. So in general, rock bursts are categorized in two classes of source mechanisms. It can either be self-triggered, which is known also as strain bursts, and are commonly associated with stress-induced spalling or slabbing at the periphery of the excavations, which is schematically shown here, or it can be triggered by a distant seismic source. This can be slipping of geological features like faults or other joints, which can transfer seismic energy to the rock mass at the excavation boundary. So the focus of this talk will mainly be on strain bursts, but we will briefly touch on this mechanism as well. The case study investigated here occurred at a Canadian mine. The actual mine layout is actually very complex, but here we have an example of the area of interest. You see some networks of the tunnels, mine tunnels, which are access to the ore body, and you also see the stopes, which are actually the ore body that needs to be excavated. So the rock burst occurred in this tunnel, which is approximately 2 kilometers below the depth. So in terms of local geology, top figure shows a cross-section through the tunnel where the event occurred. The location is indicated, where the rock burst happened is indicated by this star. So the major section of the tunnel is in basalt, which is a fairly stiff and strong unit, and far end of the tunnel is in ultramafics, which is relatively softer compared to basalt. You see the contact shape between the basalt unit and ultramafic unit shown by this red shape. There is a local fault that is subparallel to the tunnel as well. And looking from the front view, looking to the north-south here, there are also two regional faults that are also subparallel to this tunnel. So the tunnel advances from basalt into the ultramafic unit. The major rock burst that is the focus in this talk occurred within the basalt unit on the south wall, roughly 3 meters behind the ultramafic contact, which is shown by this blue between the ultramafic and basalt. The event occurred actually 2 months after the tunnel excavation was completed, but during the advancement of the tunnel itself, the drift has been seismically active with some less severe damaging events on the north wall. But the major event occurred when some drilling was happening on the lower level, and during the cleaning of these blast holes, it occurred, as I said, about 3 meters behind the contact. So to understand the local structural conditions, multiple data sources and underground observations were reviewed. So the mine has 3 global joint trends, as you see on the stereonet here. The back mapping of the tunnel in that specific drive could capture the southwest and north dipping joint sets. The left figure here shows the survey scan of the post-failure surface in the Rockburst location. From the analysis of this damage shape, 2 planar controls were interpreted, which these 2 planes agreed well with the east dipping and north dipping structures, which is globally known at the mine. And the seismic SMTI analysis from the seismic event also identified 2 potential failure planes, which are coincident with the east dipping and the southwest dipping planes. So putting all this information together, the damage incurred by the rockburst event in the south wall was associated with 2 local structures and this local fault that the geometry is representing. So for back analysis of the failure, extensive numerical modeling work was done for this mine site. The first phase of the analysis included a large mine-scale numerical model, which was calibrated using mine-wide seismic data and ground reaction observations. And the model results from that global modeling work were used to define the boundary conditions locally where exactly the rock burst happened. And then those were fed into the mechanistic modeling that I'm going to show. So you have seen this right figure multiple times in Kathy's presentation, but I really like this slide because in order to define the boundary conditions and local in situ stresses at the event location, we could follow two methods. The first one, which is shown here on the left, we could rely on regional average to initialize a constant stress state in the area of interest based on depth gradients. For the depth of the area where rock burst occurred, the stress tensor magnitudes can be generalized as you see in the table. And this is the common practice for numerical modeling. However, alternatively, we use the strain-based stress initialization method, as Kathy explained, to reproduce the complex pre-mining in situ stress conditions. So the distribution of major stresses that you see in this figure, everything is in situ. It's before any excavation or stress changes are occurring in the model. So this is the cut view along where the rock burst happened, and you can clearly see that there is a significant geological control contributing to the spatial variance in situ stress magnitudes, where basalt unit is locally acting as a stress concentrator relative to the softer units, which are the ultramafic and sediments. And also locally, you can see the stress heterogeneity between the lithology units and the faults. So this slide also shows the significance of the global modeling using the strain-based loading, actually. So we have a plan view section through the burst location, and this is indicated here for your reference, and this is the mine tunnel. And the contact, just for your reference, this is the contact between the basalt and ultramafic. So in the left, you see a constant stress tensor based on depth, and the right is actually the stresses that are sampled from the global model, which clearly shows the stress heterogeneity between two lithology domains. Now let's focus on the local model. So these figures show the geometry of the model developed in FLAC 3D. It includes three mine tunnels and two production stopes for the ore body. And this is the tunnel where the rock burst occurred. The actual gradual excavation was implemented here based on the actual advancement of this drive. One of the advantages actually of a local model would be that you can increase the complexity and add details to your model and understand the mechanisms that are happening better. So we have actually the production drills in our model because they were, the event occurred when these production drills were cleaning at the site. So this slide shows the ultramafic contact and two regional faults, which were modeled as continuum domains, but the local structures and the local fault were modeled as discontinuum interfaces. We use generalized Hooke-Brown for the regional faults, whereas for the structures, we use the bilinear Moore-Coulomb criterion. So the sequential sill excavation and support installation process was also implemented. The first 60 meters of the tunnel, which was driving within the basalt unit, had standard support, which with 3 meter debolt and 2.1 meter debolt rocks on the roof and on the walls, respectively, and an addition of 50 millimeter of fibercrete on top of it. When the tunnel was encountered by the ultramafic unit, about 16 meters of the rest of the tunnel, the ground support was modified and a heavier system was used because of the seismic activity that was observed. So 3.6 meter spin cables were added at the roof. So all of these details were implemented in the model. So for the brittle rock masses, we use the in situ cohesion weakening friction strengthening concepts. So for the sake of time, I'm going to skip this, but if there are any questions, we can discuss more on it. I just want to refer here that, again, using local models, because your scale is smaller, now you can incorporate more details and more advanced inputs in your model. So conventional shear-based criteria that are applicable for mechanisms other than brittle failure may be used in larger scale, but when you go into smaller scale, you can actually use brittle constitutive models, which is the case here. So there wasn't many detailed damage depth understandings for this case study. So to calibrate our numerical inputs, we partly relied on the understandings from literature, and also we considered the damage depths at the burst locations that were observed on site. So this figure shows the ultimate ground reaction with major principal stresses along the tunnel when all the excavations were completed. Again, for your reference, here is where Rockburst occurred. This is the contact between two lithologies, and this dashed line shows the local fault. So what we see on this figure is a stressed pillar, which stresses, indicated here, which stresses are significantly elevated as high as 90 to 120 MPa. And this stressed pillar only occurs between the wall and the local fault, that situation does not happen on the north wall. Another thing that we see, there is a significant stress heterogeneity environment developing on the south wall compared to the north wall. So these environments, this situation is happening both because of the fault and the contact between two units, stiffer basalt and the softer ultramafic. So these figures show the loads and deformations on the ground support. We appreciate the limitations of FLAC model, especially in the brittle failure to reproduce actual loads and deformations on the ground support. But we again still used these results to kind of study the relative ground behavior along the tunnel. So what was interesting is that the induced loads on the bolts and also deformations on the south wall where it is driving along the structure is significantly larger compared to the north wall where such a structure does not exist. Another interesting thing we see from these figures is that the loads and deformations within the ultramafic unit is significantly larger compared to where the tunnel is driving within basalt. So this indicated a clear strain loading on the support system in ultramafic. The mechanism was actually better understood when we looked at the evolution of the wall closure and stress front as the tunnel was advancing. So in figure A, the heading is exactly where the rockburst occurred. So the full ground reaction is about 4 rounds behind the current heading phase, which is significantly delayed compared to the typical situation in brittle hard rock masses, which typically the full ground reaction would be about 1 to 2 headings behind the advancing phase. So this delayed ground reaction continues until the heading phase advances significantly within the ultramafic. Once the heading is advanced within ultramafic, a sudden deformation increase occurs on the south wall, as you see in the figures from D and E specifically. So the conclusion from these results was that advancing from stiff basalt unit into soft ultramafic unit results in a delayed ground reaction behind the face in the excavation walls within the basalt, as the excavation within ultramafics incurs increased closure and overstraining. So we also looked at the ground reaction in detail at the burst location. I have a little bit of background of the interpretation method that we used here. So when we look at rockburst hazard potential, the damage zones around an excavation are critically important. So hard rocks, the response in hard rocks are very sensitive to confining pressures. So at the excavation boundary, when we have very low confining pressure, the damage is in macroscale because the cracks in the rock can easily propagate. So the rock volume around the excavation is highly damaged and it's actually failed. It cannot retain more load. So this zone is called highly damaged zone, or HDZ, or in literature, it's also referred to inner shell. So as we go away from excavation boundary within high confining pressures, the outer excavation damage zone is where the confining stresses are very high. So the damage is actually isolated. The rock is yielded, it's damaged, but because of the pressures, confining pressures, it's isolated. So the rock can still retain the induced loads and it's under contraction. The transition zone from the highly damaged zone to EDZ outer is called inner EDZ. And in literature, it's well understood that the strain bursts occur within inner EDZ zone. So we can focus on this location and look into our numerical models to predict the potential burst volumes. So looking into this plot, which shows the minor principal stress distributions at the burst location, a substantial extensile volume was observed in the south wall, where the low confinement environment induced and controlled by the local joints extends really deep at about 3.5 meters. So the extent of this unconfined zone is about 1 meter on the north wall. So clearly the structures here are making an unconfined zone, potential unconfined zone. On the other hand, the local structures looking into major principal stress here, the local structures on the right wall increase the volume of the transition zone, as I said, which is this orange volume, and it's the potential strain burst volume. And so it's contributing to susceptibility to increased event magnitude. So the local joints provide an unconfined or extensile situation for the stressed pillar to burst and potentially release energy at a critical point when the ultimate strength of this volume is reached. So in order to see if that critical point is reached or not, we cannot interpret or understand that from these plots. We cannot simply look at this, yes, we see a potential strain burst volume here, but we don't know if by the advancement of the tunnel, how this was failed, or either it was failed or not. So to interpret that, conceptually, the stress path evolutions in the failing rock can be used to interpret the failure intensity process, where stress hardening, as you see by this red line schematically, can be an indication of dynamic failure potential in the burst volume. So on the right, you see the stress passes that are sampled at multiple locations on the north wall. This is the in situ stress conditions. The red line shows the stress evolution within the burst volume. You see how significantly as the excavation advances, it's hardening from approximately 90 MPa to as high as 150 MPa. And then all of these induced stresses are actually relaxed, which means that this stressed rock volume released energy potentially and failed. So in order to determine the potential moment magnitude generated by the structural slipping, the slip area and shear displacement on the local structures at Rockburst location have been measured in the model, as you see in the left figures. So as it's listed in the table, the localized slip on the structure at the location of the event did not appear to be significant enough to generate the magnitude of observed macro event. So the event on the burst location was at approximately 1.3 moment magnitude, whereas the deformations and failures that we got from the model didn't introduce actually the slip mechanism to be the potential failure process. So as a summary of the causal factors that resulted into this big rockburst event is categorized in two classes, either geometry or geology. So in terms of geometry, the stress elevation at the pillar that was created between the fault and the excavation wall on the south wall was playing a major role. Then local joints increased the strain burst volume, as you see here, which is the transition zone with high induced stresses at a very low confinement conditions, and also increase the potential depth of damage. In terms of geology, virgin stress state heterogeneity before even the excavation was made as a result of stiffness contrast between two lithology domains produced a hazardous environment for the tunnel development from basalt into the ultramafic. Significant stress heterogeneity then occurred within this pillar as a result of the geometry conditions that I explained, and also the initial heterogeneous stress conditions. Loads and displacement on the ground support was elevated when driving in the ultramafic unit compared to the basalt unit that we looked into it. And one of the major influencing parameters was the direction of the tunneling, which was advancing from the stiff basalt unit into the ultramafic unit, which resulted in a delayed ground reaction behind the face in the walls in the basalt as the soft ultramafic was straining and it was increasing closure. And that concludes my case study presentation.
Thank you so much. We have questions already. Let me just bring down this so we can fit all. That's fantastic topic. I'm sure that we're going to have many other viewers later because we are just before Eastern, but I'm sure that people will join and watch later. We have many people saying good night, good evening, and saying that's really a very interesting topic. And we have some questions here already. So we have our one of the directors of CBT, Jean-Pierre. He's from the Valley, from this big mining company. So he has already something. So here at Valley, in our tunneling standard, giving the general issues related to predict when and or where a rock burst can occur, we have specified intensive microseismic investigation. So it's a comment. And then here comes the question. It's a long one. And pilot tunnels when some conditions are met. Do you believe it's a good or the best possible way to prevent consequences on workers and equipment to use the microseismic investigation?
I can speak to this question because it is a question. I think that using microseismic investigation and pilot holes or pilot tunnels to gain knowledge of what you may encounter before a tunnel advances provides an incredible opportunity to predict what type of hazard may be encountered. And that ability to predict conditions and hazard mechanisms helps us to develop the controls required to prevent consequences for workers. And those controls may be design controls through how we excavate a tunnel or drilling and blasting procedures. It may be design controls around how we design our ground support systems. And we can also develop important operational controls to mitigate hazard around exclusion zones to keep workers away from dangerous areas, or the utilization of equipment to offset people from high hazardous conditions. So the tools that you speak of, the microseismic monitoring and the use of pilot tunnels to collect information, gives us that critical knowledge that can be used to develop the controls. And I like that Valley is standardizing these approaches, because when we work in mining operations, if you standardize expectations for the type of data to be collected and the methodology for analyzing that data and using that data for design, that ensures that our workforce, our operations workforce, and also our engineering workforce have the corporate support and the tools available to really add maximum value to worker safety.
So, and when you're basically, it's a real-time operation, right? So you have your team there, like before you open the mine, you do a model, and then you do the instrumentation, and you have to update your model, like keep updating. It's like continuous work, basically.
Yep, absolutely.
Yeah. And do you have, like, for example, do you need to be on the mine, or you have also access to all this data? Like you can be in Kingston and the mine is further away and you have full access and you can be updating continuously your model.
Yeah.
How is it?
But both of those, right? We have our microseismic systems that are working in mines and our data collection that's working in mines. And we can transfer all of this information over the internet and do analysis from the other side of the world if that's necessary. But when you're doing analyses remotely, you need to have a really good relationship with the people working at the mine so that there's clear communication, constant data transfer, good trust between the people working remotely and the people working on the site.
Yes. So your team is both in the office and in the mine.
Yeah.
Okay. There's more question here, but Dalma, you have a question before I go to Gabriel?
Yes. Well, first, thank you, Dr. Neda and Katie, for this excellent lecture. Well, I have a question on the slide number 34. If you could please go back.
Let me see.
My question is, what would happen if you would continue with constant in situ stress? So
Right. Yeah. Yeah, that's a great question. So here you clearly see how stress heterogeneity is underestimated if you take a simple understanding of stress conditions before the excavation is done. And I actually have, because of the time, I didn't have those slides here, but now that the question is here, I can show some cool plots. So I have this here. This is showing the model results where the complex in situ stress was used and I presented during the talk. And these are showing when you just include the constant stress condition. So you can see how significantly the depth of damage will be underestimated. And this is a very important input. Understanding the depth of damage is an important parameter for ground support design for many controls that you would plan to take. So simple stresses can underestimate this understanding. The volume of the potential rock burst is dependent on your understanding of this depth. And also you can see that here, as I presented, this is the burst volume where I called it the inner excavation damage zone. The complex in situ stress model could predict that zone, whereas when you have a constant stress, you would simply miss that zone. So this doesn't show the potential hazard. If you want to use this model for forward predictions, for later predictions in other areas of the mine, using that simple understanding, you would miss predicting the potential hazard. I probably have another cool slide here. So this is showing the stress path within the burst volume. The red line is what I show in my presentation, but this dashed line is the stress path exactly on the same spot when using the simple model with simple stress conditions. And you see it's the induced stresses are way smaller than the complex condition. And as I said, the failure process, which actually is a warning that this burst volume can fail, is not captured with simple models.
Thank you.
Thank you.
So here, talking about stress, we have a question from Gabriel. Is there much difference in the modeling process in tectonically active versus passive scenarios? Like it's more challenge, perhaps?
Okay. I think if you were referring to tectonic where you would have natural earthquakes, the process for numerical modeling does vary a little bit because you need to account for potential earthquakes in your boundary conditions. And this is normally done by applying static acceleration loads as a boundary condition to our numerical models. It's important to recognize that natural earthquakes that could impact an excavation are generally larger magnitude, but much further away. And so the waveforms attenuate, they're low frequency, and they don't generate the same energy, the same peak particle velocities as a near field seismic event that would be induced by an excavation activity or by a mining activity. So the hazard actually changes. And so we can often tolerate doing that static acceleration loading rather than dynamic loading. That's a generalization. Sometimes it may be appropriate to put a dynamic load in if you're in an earthquake-prone area.
Thank you. I think we don't have more questions. However, I would like, because here it's very different environment than Canada. So I get always very curious when I was, so here they're saying thanks for you. And so I get very curious about the life, like going the mine in Canada, and I heard some stories when I was studying Kingston about bear, and that's a bit dangerous, or like it is super cold and so on. Have you guys already like encountered a bear while going to the mines or doing some exploration?
I've seen foxes.
Okay, foxes, beavers.
I've seen those, never
And
bears.
the bear, Kathy, you met a bear once, is that right?
I've seen lots of bears working in Colombia doing mine closure work where you kind of have to hike around in the bush You have to be aware of bears. And then I've also worked in operations in the Arctic where sometimes they have polar bears. And in these cases, they actually kind of shut down. So nobody's allowed to go outside if there's a polar bear in the area. Fortunately, it doesn't happen very often, but and they also have to shut down sometimes if it's too cold. Like if there's a big snowstorm or a blizzard, it could be dangerous to go outside. But that's in the very far north. Most of Canada is not like that.
And how cold what was the coldest you've been in a mine or in the Arctic, no, for operation? What was the coldest? That was summer, I guess, but still cold.
Yeah, I have a -40 experience, which was actually, I was there for a job interview and I was like, this is not nice.
Okay.
Not a good time to come here. But everybody warned me back then, like, this is not a good time for job interview to be on site. Like, maybe this is a typical situation here. But yeah, it was in Arctic, very far north.
And the deepest mine, what was the deepest, like down there, down in the earth?
I've been to about 3.5 kilometers.
Wow, 3.5 kilometers. Wow, that's a lot. And Jean-Pierre, I think he's inviting you guys to Brazil. We often encounter anomalous stress in our basalt tunnels in the south of Brazil, despite the low depths with rockburst behavior as well. It's a good place to test the model. He's inviting you guys to come here, visit Brazil, do some modeling for Vale. So he said, I can send his contact, so he can take you around the basalt.
Sounds good.
Sounds good. Thank you.
Okay, yes, indeed. Okay, he's really inviting you. Okay, thank you so much. Thank you for the presentation, for answering the questions. And then this video is going to be available in our YouTube channel. Thank you for the Dalma for being here to represent CBMR. We have more webinars coming up. We have Andrea Mengi, and we have Yanis that's going to talk about the non-destructive methods, that's mechanized tunneling, small diameter. And yes, and we have many events coming up. So people also talking, giving you thanks for the presentation.
Thank you for
So
the
I give the space for the last words for each one of you. If you want to say something or just happy Easter to everybody. Let's eat lots of chocolates.
Thank you very much for the opportunity. It's been lots of fun. Certainly.
Yeah, thank you, Daniela. When you texted me, it was great hearing back from you again. And also, this opportunity was great to present some of our work. And yeah, happy Easter to everyone.
Thank you, Dalma. So, okay, so maybe see you guys in 2026 in the WTC Canada if they want.
Awesome. Bye.
Bye. Good night. Thank you, everybody. Bye.
Bye.